Okay, complex ion equilibria. So transition metal ions often can be good Lewis acids, so electron acceptors. And the one that we've looked at is iron 3, acts as a Lewis acid. Water molecules connect as Lewis bases. They can donate electrons because oxygen has 2 lone pairs in water, right? So the water molecules can come around and hydrate the transition metal ions. So here, silver ion is hydrated in solution. It's got 2 water molecules around it. So it's not really silver ion all by itself. It's accompanied by 2 water molecules. And this is called a complex ion. It's a complex ion because it's not just a single element here. It's not a single covalently bonded polyatomic ion. You've got multiple things coming together, but it's still an ion because overall it has a charge. So you've got a central metal ion, and then you've got 1 or more ligands. So the things that are attached to it are called ligands. So in this example here, water is a ligand. It's a neutral molecule. It can also be an ion, but it acts as a Lewis base. So it's something that's donating electrons to that metal ion. If you add a stronger Lewis base, it will displace the water because you've got the metal ion acting as an acid, and it's going to prefer the stronger base. So adding ammonia, which is still a weak base, but it's a stronger base than water is, that will displace the water molecules, and you'll get this silver with 2 ammonia molecules as the ligands. Now, when we look at that, for simplicity, we usually leave water out of the equation because if we calculate an equilibrium constant for this, the water isn't going to show up anyway because it's a liquid, right? It's not going to be in there anyway. The concentration of this complex ion between silver and water is going to be the same as the concentration of just silver ion, and so we don't really need to have the water in there. So we can calculate an equilibrium constant for this. It's this complex ion with ammonium divided by the concentration of the silver ion and the ammonia squared. And this is called a formation constant because it's an equilibrium constant describing the formation of a complex ion. So there's a table of formation constants. Lots of different complex ions are possible. Okay, let's do a problem. You mix 125 milliliter sample of a solution that is 0.0117 molar in nickel chloride with a 175 milliliter sample of a solution that is 0.250 molar in ammonia. After the solution reaches equilibrium, what concentration of nickel 2+ remains? And they're giving us the formation constant for this complex ion. I would not expect you to know what complex ion nickel forms with ammonia. How do we know it's 6? Well, if you go look it up in the table, hopefully it's in here. Yeah, there it is. The only complex ion here between nickel and ammonia is NiNH3,6. So that's how you would know. You would just find that in the table. So we can write an equation describing the formation of that complex ion. Nickel 2+ is going to get together with 6 ammonia molecules and form the complex ion. You okay with that? So we've got things mixing here, and they've given us the volumes, and so we do have to consider the total volume of everything. So our total volume, after mixing these things, we've got 125 plus 175. So that's going to be 300, right? So 300 milliliters is our total volume. We're given the concentrations of the solutions that were mixed, and so we need to find out how many moles of nickel chloride, how many moles of ammonia, and then divide by the new concentration. So for the nickel, we had 125 milliliters, and it was 0.0117 molar. So that would give us moles of nickel, and then it's being diluted, right? So divide by 300 milliliters. And that'll give us the new concentration. So that's for the nickel. Does that make sense? Or is that putting too many things together? Let me show you sort of a longer way with the other one, with the ammonia. So we have 175 milliliters of the ammonia solution. So that would be 0.1750 liters, right? And if we multiply that by the concentration of the ammonia solution, 0.25 moles per liter, that's going to give us the moles of ammonia, right? So 0.004375 moles. Wait. Too many zeros. Just 0.04375. And then to get the concentration, what do? Divide by the volume. So we're going to divide by the volume. The new volume is 0.3000 liters. So we take that and we divide by 0.3, and we get 0.1458 molar ammonia. So I converted liters to milliliters to liters. I multiplied by the molarity to get the moles. I divided by the new expanded volume to get the molarity. It's actually the same thing that I did up here. And you can think of this as M1V1 equals M2V2. V1 times M1 divided by V2 gives me M2. I've got the volume times the concentration. That would give me millimoles. Divide by the volume in milliliters, and it gives me molarity. So we're going to start out here with 0.004875 of the nickel and 0.1458 of the ammonia. And then what's going to happen? It's going to react, right? and form the complex ion. So we can think of this with a nice table. So we're going to lose X here and lose X there. And originally we had none of this complex ion, and we're going to gain X. So Kf, the formation constant, is the concentration of the complex ion divided by the concentration of the nickel ion and the concentration of ammonia to what power? To the 6th power. Ah, that's what it is. Mm-hmm.
Wouldn't ammonia be -6x?
Haha, yes, thank you. Yeah, no, you gotta yell at me when I do stupid things like this. Yes, it's -6x, right? Because there's a 6 here.
Sometimes I doubt myself though, and I'm like, maybe I don't know.
Yeah, I get that. But then just ask me a question. Because, yeah, especially today, there's going to be a bunch of mistakes. I've already made a whole bunch of them. Okay, that's better. Okay, so we're going to have kind of a mess here, aren't we? I mean, we could try X is small. You want to try X is small? Doesn't hurt to try it. Let's try X is small. So then we've got 2.0 times 10 to the 8th is going to be equal to X divided by 0.004875 divided by 0.1458 to the 6th power. I don't think X is going to be small, but we'll see. So that gives me X being about 9. X is not small, right? X is huge, so we can't do that. But it didn't hurt anything to try. So that leaves us with a very messy polynomial, doesn't it? We're going to have X up here, and then in the denominator, we've got 0.004875 minus X, and the quantity 0.1458 minus 6X to the 6th power. This is a job for the solver. Okay, didn't like that. Okay, so we had a little bit of off recording discussions about this. And people that got their solvers to work were getting an X of, about 4.8 times 10 to the minus 3. Then when you're subtracting it from the nickel that's going to be extremely close. And I've already put in extra digits here that are not significant figures. So this isn't working very well, is it? So one thing we can do is say, well, this K is really high, right? Let's assume that everything reacts that can react, and then let's see what comes back. Does that make sense? So I'm going to look at this. I've got 0.004875, and I've got I need 6 of these, 0.1458. Let's calculate how much of this is needed to react with this and make all of our nickel into this. Does that make sense? So for 0.004875 moles per liter of nickel, if I multiply that by 6, that's going to require 0.02925 of the ammonia. Okay, so I'm going to get rid of our wrong stuff here. What we're doing is very much like the beginning of the titration, where we're adding so I've got this and I'm adding this, and so this is going to we're going to use up all of this. And we're going to use up, what did I calculate? 6 times that. So that's going to go to 0. This one's going to go 0.1458 minus 0.02925. This is going to be 0.11655. And this is going to increase. All of the nickel is going to become this complex ion, 0.004875. So now let's use these concentrations as our initial values and see how much goes the other way. So this is going to lose 6. This is going to gain 6. Lose X, gain 6X, and gain X. Now I'm really regretting keeping so many digits. Okay. Now, do we think that maybe X will be small? Yeah, because this equilibrium constant is very large, which means this goes very far to the right. It's mostly product. Very little of the reactant left. And so the amount of, if we started out with this, the amount that would come apart would be very small. So let's try the X is small and see how it goes. So using X is small, then we've got 4875 divided by X times 0.11655 to the 6th power. And so that's a little easier to solve. 0.004875 divided by 2 times 10 to the 8th divided by 0.11655 to the 6th power. And X is 9.7 times 10 to the minus 6. Is the exismal approximation valid here? Is this small compared to this number? Yeah. You can do the calculation, but it's less than 5%. Uh-huh.
Where did the 0.02925 come from?
That's an excellent question. So what I did here is I was doing stoichiometry, and I'm saying if I have all of the nickel react, how much of the ammonia is going to react with it? Well, 6 times as many moles. So I took this number and multiplied by 6.
Okay, so that's when.
And so that's why I'm getting rid of that much of the ammonia.
Okay.
Excellent question. So this came up with 9.7 times 10 to the minus 6 molar. The book says 9.6 times 10 to the minus 6 molar. We'll call it good. Any questions?
Any particular? I'm just curious as to why it didn't work the other way. With the solver.
Yeah, why didn't it work the other way? That's an excellent question. I must have gotten something typed into my solver incorrectly. I think what happened is that X ended up being so similar in size to this number that that when we subtracted, the difference is too small, right? Because the difference should be 9.7 times 10 to the minus 6, right? And so we don't have enough precision in this number to be able to subtract and get that small of a number. So doing equilibrium calculations, you want to go to the side that's favored and then work the other way. And I didn't think ahead, but I think it ended up being an okay object lesson. Because we tried one thing and it didn't work. So then you try something else. Any other questions? So the solubility of an ionic compound will be affected if the metal cation in that compound forms complex ions. So the most common Lewis bases that increase solubility will be ammonia, cyanide, and hydroxide. So if we look at this complex ion formation between the silver and the ammonia complexes the silver ion, and so it increases the solubility of the silver chloride. Adding ammonia changes the equilibrium constant for the dissolution of silver chloride by a factor of 17 million. It's a little bit of an increase. Huh? Do you know why people use ammonia for cleaning? It stinks really bad. It increases the solubility of ions by complexing them. And when things are soluble, you can wipe them away. So you add the ammonia, and this relatively insoluble silver chloride actually becomes quite soluble. Now we've got an equilibrium constant of 3 times 10 to the minus third, which is very, it's still small, but it's significant. Metal hydroxides, a lot of those are insoluble or slightly soluble in neutral water, right? But they become much more soluble in acidic solution. Some metal hydroxides are amphoteric. They can also act as acids, which is sort of counterintuitive. but that increases the solubility in basic solutions. So here's the aluminum hydroxide. It can actually act as an acid and accept the electron pair from the hydroxide ion to form this complex ion. So aluminum is really funny stuff because it's soluble at high pH and at low pH, but it's insoluble in the middle. Because at low pH, higher hydrogen ion concentration, the aluminum hydroxide is insoluble. I'm sorry, it's soluble at, I should rewind, but I'm not going to. When there's no hydroxide present, the aluminum's soluble. You get into the middle where you've got hydroxide and it precipitates, it's insoluble. You add more hydroxide ion and then it forms a complex ion and is soluble again. Very strange. So you put aluminum ion in solution and it will form a complex ion with water. So that is, and we learned about this, that's not chapter 17, it's chapter 16. Yeah, I changed that wrong, sorry, chapter 16. We talked about the small highly charged cations, aluminum 3 and iron 3. And so it becomes hydrated, and then it can lose a hydrogen ion to form a hydronium ion in the water. So it's acidic. When we add base to this, it will drive the reaction to the right by removing the hydronium ions that are formed, right? So we add hydroxide, and it will pull off another one. And more hydroxide will pull off another one. When so this then is insoluble here. That's equivalent to aluminum hydroxide. As we add more base to this, because this isn't confusing at all, is it? Gosh. So we've got 3 waters here and 2 waters, and now we've got 2 hydroxides. Here we had 3 hydroxides, but now we have a negative charge. So the hydroxide ion pulled another hydrogen ion off of the solid, and that causes it to be an ion again, and it dissolves. So acidic solution, you've got the hydrated aluminum, it's soluble. pH neutral, now you've got the aluminum with hydroxide ion and water molecules, and the charge on this is neutral. It's not an ion. It's going to precipitate. You pull more hydrogen ions off, and it becomes a negative ion now, and it'll be soluble again. There are several cations that can do this: aluminum, chromium 3, zinc, lead 2, and tin 2. So they form amphoteric hydroxides. They're hydroxides. They can act as a base, but they can also act as an acid. The extent to which a metal hydroxide can dissolve in both acid and base depends on the degree to which it is amphoteric.